Okay. Good morning, everybody. My name is Nicholas Weichert. I worked on this project alongside Rudy Martinez, Hector Martinez, Jansen Kawo, and Veer Patel. Our project is ultrasonic object detection, and it is a TI-sponsored project. The purpose of this project is to expand on TI's current gas metrology library to add the functionality of distance and angle calculation of objects up to 13 feet away. The hardware that we use for this project is the MSP432, an unreleased prototype booster pack, launch pad, and 40 kilohertz ultrasonic transducers. The intention of this project is to tackle an adjacent market for their current library that involves occupancy sensors, standalone air conditioners, and garage door sensors. So for the POC of this project, we worked on redesigning and integrating a garage door sensor using ultrasonic transducers.
So the current garage door sensors uses IR transmitters and IR emitters. And in this system, if the signal is not received by the receiver, while the garage door is closing, it immediately reverses the direction of the garage door. In our system, the ultrasonic transducer emits a signal, and the echo reflected from the object is collected by the second ultrasonic transducer receiver. And based on the signals received, the location information of the object can be collected, and it can be used to reverse the garage door.
Here is the hardware design. We use two pairs of transducers, an MSP432 and a booster pack. The initial setup, we used a putty to secure transducers at 3-inch apart, and the case design is a prototype for transducer inside the garage door. How we calculate distance? The transmitter emits signal, and after a certain period of time, the receiver capture back. Based on the time of flight between the sensor and an object, and using the speed of the sound, we're able to calculate the distance. How we calculate an angle? We use another pair of transducers to calculate the second distance, and out of that we use triangulation formula to calculate the angle between the sensor.
As Jonathan just mentioned, one transducer sends out a certain number of pulses while the second one receives, which is our UPS signal, and after a certain time the transducers switch. Now the second transducer sends out the same number of pulses, and the first one receives, which is our DNS signal. The third plot on the left is the correlation of both initial signals, which effectively filters out noise and allows us to extrapolate any required data from it. From our results, we have two lines. The blue one is a comparison of the simulated and actual distances of the objects, which should be linear, and the orange is the percent error of these distances. Our trials consisted of a placement of the sensor pairs at 3, 5, and 8 inches apart, with a varying distance placement of the object. And from our recorded data, we can conclude that our 8-inch apart configuration gave the best distance and angle with 90% accuracy.
Our scope of the project was to detect the object within 13-foot range. Our latest configurations detect an object up to 5.5 feet. This is only limited to flat surface objects, but most of the objects can be detected within a 4-foot range. Currently, we are moving towards implementing the MATLAB code we used for offline calculations onto MSP432 and embedded C to handle real-time operations. Thank you. Moving on to questions.
So, kind of related to the last thing you just mentioned, that you're currently able to do flat surface objects. Don't ultrasonics typically have issue with soft targets, I guess, and receiving them, or am I confused on that? So my concern is if you're using it to stop a garage door from opening and there's something soft like baby, dog, clothes, blanket, will it be effective? And you don't have to know that now because you're still working, but just kind of your thoughts.
So that was one of the things. Sound travels at different speeds through different mediums, and it can absorb or it can reflect.
Exactly.
What we found was for any objects we tested with, cups, hands, clothes, balls, and coasters, just every object that we could think of, and it reflected back a good, just a good reflection. We were able to capture the data and figure out an angle.
Perhaps
for that.
Big city.
Right.
Yeah.
I'm just trying to see your numbers compared to what is out there right now in the industry, what your improvement you're giving.
So just for numbers, the current system uses IR, and it just goes across the garage doors, and then if your hand goes in, the signal interrupts, and then it just immediately reverses. That goes across the whole garage door, which is 13 feet, which is our objective. The gas library that was given to us from TI was meant for flow sensing, pressure sensing, and level metering. So basically they took the transducer, put it up to a pipe filled with gas or liquid, and it emits a pulse, and then they can capture information relative to that. So they have it hard-coded and set as a constraint of the system to only work for a couple feet out. Our system, we are trying to adapt and give it more energy to go further. So when we can get to that in the phase 2 next semester, then it'll meet the same range that the IR sensor does, with using less power, because ultrasounds only have to emit, they don't have to constantly send out a signal. It'll be cheaper to construct the system, and it will, there was one other thing.
Less power?
It's less power, it's less money, there was one other thing, I don't remember what. Oh, it's the benefit, obviously, of distance and angle detection.
Confirmation.
All right, let's thank the group.